Okay, this week is tropical weather. So we're going to deal with conditions that are in the tropics, basically where no fronts really occur. And with that, main focus will be on tropical cyclones. So the weather in the tropics is anywhere that the sun directly moves overhead. So that's basically 23.5 degrees north, 23.5 degrees south. There's very little change, not much change in temperature. Matter of fact, the daily variation in temperature from high to low that day is more than between each month. So basically the air mass is pretty uniform, very warm, very humid. So thunderstorms may develop and they may actually line in tropical non-squall clusters or more intense cells. And they look like mid-latitude squall lines, and they develop particularly along the intertropical convergence zones. Think about it. It's called a convergence zone for a reason. The air comes together there, thunderstorms develop. One of the interesting things that meteorologists do is do a streamline analysis on a map. Streamlines are just, you start with a wind point and you just try to follow the wind, drawing a line. And because you're not doing a pressure or an isobar analysis, you can actually see convergence or divergence areas fairly well, picking up with a streamline analysis. Hurricanes are a part of the tropics. They develop in the tropics typically and move northward. They're very intense cyclones. They're tropical cyclones. There's a difference. We've studied extratropical cyclones. Now we're going to talk about a tropical or warm core. Hurricanes originate under uniformly warm, humid air masses. In other words, extratropical cyclones have a major temperature contrast across them. Hurricanes do not. Matter of fact, they hate temperature contrast. They will die when they get into an area that has temperature contrast. A hurricane typically can be much smaller. Many extratropical cyclones may be 500, 1,000 miles across. Hurricanes are some of them are as tiny as 75 miles across. Central pressure is much lower in a hurricane typically than in an extratropical cyclone. So all these, and guess what? Hurricanes weaken with height. There are many times that there is an anticyclone on top of a hurricane. Here you can see the eye of the hurricane. Something called a stadium effect. Sometimes you get in the eye tremendous thunderstorms that look very much the same, but in the eye itself, almost no clouds. Here is an example of an eye of a hurricane and the thunderstorms around it. Let's move on to just think about this wind. See how there's spiral bands out here, out from it. In the eye, the air is actually descending. And some of the high altitude winds are blowing the air out away. So there's divergence over top of the storm. So if you look at this storm here, here is a very classic major hurricane. Look at the spiral bands. Here's one. Here's another one. Here's another one. Here's another one. Here is the eye. So if you have a hurricane approaching you, what you're going to get is a line of showers, maybe thunderstorms with the first spiral band. Oh, then you're going to get dry. Then there's going to be another one. Each one of these will have increasing wind and heavier rain many times. So finally you get into the eye of the storm, around the eye wall, and get very intense rain, and then all of a sudden it's over. You're in the eye, and then it begins again, the same process. Slowly working your way out through the outer bands here, this one. So that's what we look at when you look at this very intense hurricane. You see all these bands, winds are blowing into the circulation. They're counterclockwise. So you wind up getting very intense thunderstorms along each of these bands. So what are some of the necessary? You need high sea surface temperatures. We're talking above 80 degrees. And it's got to be that warm at least through 150 feet down into the ocean. That takes a lot of heating. You're not going to get that further north in the Atlantic, for example, or further north in the Pacific. that's going to be developed, these storms down either in the tropics, maybe along the Gulf Stream. The Gulf Stream is pretty warm, pretty deep. And the strong tropical cyclone winds can induce the Ekman effect, which might lead to lower SSTs along a path or under it. And you can see here the loops. Very warm air, warm, very humid, and also very warm conditions that develop along the Gulf Stream. And you see these little eddies of warm water. Many times you'll see hurricanes might develop, they move across the Gulf Stream, they actually intensify because the Gulf Stream is fairly warm, maybe times warmer than the central part of the Atlantic. And the Gulf of Mexico, well, that's just some of the warmest water on Earth. So that's why sometimes hurricanes can really fire up in that area. You must have a Coriolis effect. The Coriolis effect, what makes the wind turn to the right, it makes it goes in a circle. So if you're down below 5 degrees north or south, you get too close to the equator, you don't have the Coriolis effect. So what happens is you don't get these circulations develop. You may get thunderstorms, but you don't get a hurricane. Where and when? Well, there are numerous thunderstorms. Notice that over the Pacific Ocean, there are actually more hurricanes and tropical cyclones that develop than over the Atlantic in a typical year. So there are actually more in the Pacific Ocean than there are in the Atlantic. However, in the Atlantic, we average 12. I think it's now gone up to 14 in a year, because last year we just updated that. So many hurricanes in a series. And major hurricanes are a hurricane that is greater on the Saffir-Simpson scale of 3 or more. And we're going to talk about that scale here in a little bit. It's a wind scale. And here you can see where they typically form. Notice, hurricanes that develop off of Mexico down in the eastern Pacific Ocean, or the west, actually move towards the west and away from the United States. That's why California and those areas don't get hurricanes. Also, the water's fairly cool around California, so it's not going to get much. And here you can see this season. We've had hurricanes in almost every month, except maybe February. And even then, there have been a few times where there have been possibles. And you can see the peak occurs typically late August into September, early October. And notice how they progress. They're going to progress in areas that have the warmest water temperatures first. Well, the Gulf of Mexico is fairly shallow. It heats up very quickly, so that is the first area. Right along that area in the Gulf Stream is where the first places will develop. And with time, the ocean itself is heating more larger areas develop, and then it gradually diminishes in the fall. Many hurricanes form from easterly waves. Easterly waves develop thunderstorms along their path. The circulation begins to develop within that area of thunderstorms, and that develops eventually possibly a tropical depression, and then maybe into a tropical storm, and eventually into a hurricane. There are things called the Saharan air layer. We've talked about hababs. Well, guess what? Hababs occur in the Sahara. When they occur you get a very intense thunderstorm, pushes very cold air down to the ground. Of course, it's so dry over there that no moisture is reaching the ground, and you wind up with dust getting blown up into the atmosphere. And these dust layers can move all the way across the Atlantic Ocean. When they do, these are very stable. They have tremendous wind shear within them, all of which, and they're also very dry aloft. So you wind up with no thunderstorms able to really tap into that moisture that's all below there. You wind up killing hurricanes. Hurricanes basically have a life cycle where the pressure begins to fall and you begin to set the circulation. Hurricanes need a lot of water vapor, and all this releases that latent heat. That is the driving force of a hurricane, and an expansional cooling from that. You're raising the temperatures in the storm core and diverges the air aloft. Here is your wind speeds. Tropical depressions, which are not named, need at least a maximum sustained wind of 23 miles per hour or higher. So that doesn't take a whole lot to get a tropical depression, does it? But a tropical storm, you need 39 miles per hour or greater, and a hurricane needs 74 miles per hour. And you can move up and down in that system depending on how the storm reacts. Here are the hazards from hurricanes. One of the biggest hazards is storm surge. I actually live not far from the ocean, far enough that I'm protected. I checked my house out, and it would take a storm surge here of at least 15 feet to get to my house. And the highest that I can find that has ever occurred around here is around 12 feet. And that occurred back in the 16 and 1700s on some historical storms that occurred then. You can see rain is another big issue. So when you have this hurricane coming in, what it's doing, think about it, has a counterclockwise circulation. So if the hurricane is coming in south of you, the winds are coming from the east into your area. If I have 100-mile-an-hour winds pushing on the water, it's going to move a lot of water. All that water's got to go somewhere. Where it's going to go is hit the coast, and it's going to pile up on the coast and gradually find a way inland from the coast. That's what causes the tidal surge or the storm surge, causing the major flooding. Also rain. Think about it. Hurricane forms in a very warm, very moist environment. It produces tremendous rainfalls. And when they get stalled out, like Harvey did, and just sat there for a while, it really produces ridiculous rainfalls. So the pressure gradient force is what causes the wind. There is a very, very tight pressure gradient in the middle of the hurricane, and that is what increases the wind speed. And there can even be spin-up vortices within the middle of a hurricane. And the winds diminish rapidly. Remember, a hurricane needs moisture, and it needs warm ocean temperatures. Well, it doesn't get that over land. Oh, yeah. And a lot of times over land, there may be a cold front coming in, especially if it's moved north. Oh, yeah, it doesn't like cold air either. So all these things play into the fact that hurricanes can reduce in intensity very quickly. Storm surge, as I mentioned, can be a dome of ocean water pushed inland, and it can be responsible for a lot of fatalities, unfortunately. People want to stay on a barrier island maybe to watch this fabulous looking storm come in, or they don't want to leave their home of 20 years. And here comes this storm that's never before have they experienced one that went to their south. And all of a sudden, all this wind pushes in, all this water raises the whole sea level up, maybe as much as, in this case, 15 feet. And you wind up with waves on top of that of 15 to 20 feet. The house doesn't stand much of a chance, does it? Spectacular damage, almost nothing left where it came inland. And Camille was another one that came in with 24-foot storm surge. Imagine how high that water became in that area. Katrina devastated New Orleans. Sandy, which you're going to write a paper about to me, it had tremendous storm surge that came into Long Island and New York City, causing a lot of problems. There are now computer-generated models for how to forecast storm surge. I worked on some of these when I was in the Weather Service. The slosh model, for example, it does a great job of giving you estimates of the maximum storm surge from any hurricane and where areas might be flooded from that now. And hurricanes are getting stronger. And why is that? Well, there's an Atlantic multi-decadal oscillation. We are in a warm phase of that right now. And it has occurred in the past, and we seem to be having an enhanced phase of it right now. But the Atlantic Ocean is warmer than it's been normally, and by being warmer, has more heat stored. Being more heat stored, it allows more hurricanes. El Nino and the ENSO. El Nino, when El Nino occurs, the warm phase, what it does is suppresses hurricane activity. What it does is increased winds. Part of El Nino is to increase the winds in the tropics. When it does that, hurricanes don't like wind shear, so you wind up with less hurricanes. But La Nina, on the other hand, weakens the winds in the tropics, so La Nina would give you more hurricanes. And this is the conclusions from the World Meteorological Organization of what happens if we continue to warm. We'll have more higher storm surges because the ocean will be rising, the sea level. The tropical cyclones will tend to be stronger, but they may not necessarily be as increased number of them, but there may be a greater proportion of them that reach Category 5 hurricanes. Back in the 70s and 80s, there wasn't a hurricane to be found along the East Coast or Florida coast of the United States. Interestingly, when I was in college, we all wanted to go see a hurricane. And we set criteria that we would drive so many hundreds of miles to go find one. The whole 4 years I was there, we had not a single one occurred within that area. Barrier islands protect inland. Barrier islands, like along the Outer Banks, protect the inland part of North Carolina. They can get destroyed during hurricanes, the outer bands. You can see here, inlets were cut literally in these barrier islands. But we like to live on barrier islands many times. We have some around my area. There are some here. Some of these barrier islands even were formed through hurricane processes. Evacuations are a major hassle. It is estimated in Hampton Roads area it will take 3 to 4 days to evacuate the area from a Category 3 or higher hurricane. So you can see the issues. There's over 1.5 to 2 million people living here. That would be a major hassle for all the roads to handle. Some strategies to minimize, get people to move out of an area or higher elevations. And they've been predicting each year what the long-range forecasting of hurricanes is, and they issue in a seasonal outlooks as well. Way back when, they used to try to modify hurricanes and discovered they weren't doing a very good job of it. One of the things was that they wanted to issue silver iodine. So what they were trying to do was increase the number of ice crystals in the hurricane. Hurricane's warm. It doesn't have that many ice crystals in it. And they discovered that, when eye walls actually change shape anyway. So they had no success with this. So the last thing I wanted to just quickly show was a map of all the storms. And you can see here, data extends back into the 1850s. Look at all the storms that have occurred out in the oceans. Many of them beginning off of Africa, coming up, others in the Gulf of Mexico. And look at them all along the Pacific out here. And how none of them, almost none, make it up into California. Sometimes some of the moisture might, but not much. So this is just where these form in the tropics. So if you have any questions about all this, please don't hesitate to ask.